Alright, so in this video I'm gonna be explaining another important article with the title Random Walk Conformer, Learning Graph Representation from Long and Short Range. So this AAAI article in 2023 from Taiwan University. While graph neural networks have achieved notable success in various graph mining tasks, conventional graph neural networks only model the pairwise correlation in one-hop neighbors without considering the long-term relations and the high-order patterns, thus limiting their performances. Recently, several works have addressed these issues by exploring the motive frequent subgraphs. However, these methods usually require an unacceptable computational time to enumerate all possible combinations of motifs. So in this paper, we introduce a new GNN, namely random walk conformer, to exploit global correlations and local patterns based on the random walk, which is a promising method to discover the graph structure. So it's a GNN framework, but it uses random walk. Besides, we propose random walk encoding to help random walk conformer capture topological information, which is proven more expressive than conventional spatial encoding. So our task could be either regression or classification. We have aggregation and update in our classical message pathing. And now the transformer is also interested related to this, because if GNN is in one extreme, the other extreme is graph transformer and transformer. So we are somehow here that we are combining random walk and GNN, which is capturing some topological aspects. And the method is random walk. First, we do random walk encoding, while the output of GNN or transformer is permutations invariant to input data. It is fundamental to encode the auxiliary topological information by spatial encoding. Therefore, previous works introduce spatial encoding. So, however, previous relative spatial encodings are typically based on shortest path between two nodes, which only considers a fixed single path on the graph. Therefore, we introduce random walk encodings which exploit the relative position between two nodes by multiple paths from the random walk. Generally, the random walk sequence is a length node sequence sampled from a graph. A random walk sequence in a graph is generated by starting on some initial node S1 and iteratively sampling the next node S1, S2, and then Si randomly from neighbors. And since the nodes on a sparse graph are with a small degree, the uniform sampling on the neighborhood set tends to backtrack often and is challenging to discover long-range patterns. To explore further nodes, the random walk is sampled by non-backtracking methods. For example, excluding the previous node unless it is the only neighbor. This part, I've seen some papers use the term repelling random walks. So if it's like ants, opposite to ants. Ants just follow the pheromones, but now because they know this path has been tracked, so they try to They try to explore new ways instead of going back to the things that has happened before. So given a random walk S, the random walk distance defined is the distance between two nodes, so which represents the shortest distance between two nodes in the random walk. We can find different paths by sampling multiple random walks to discover more diverse patterns between a node pair. Note that the shortest path encoding can be regarded as a special case of the random walk encoding with infinity walk length L to cover the whole graph. So similar to other spatial encoding, we train the embedding function like this, which is a map distance between two nodes. And also we have trainable parameters as our random walk encoding. So we can convert a random walk sequence, for example, a simple line graph to a motif by utilizing the global topological information. You see the architecture of this random walk conformer, that the model is composed of several random walk conformer blocks. Each block consists of a feed forward, this feed forward, and a random walk self-attention. So this is a block that has self-attention, network, self-walk convolution. So all of this is just one block. Then you can make it cascaded and then you have a multi-layer. But look at this, that it has random walk self-attention and it has random walk convolution. So we are just sampling and then giving you to feed forward. So this is how we are embedding. But let's focus on self-attention. Conventional GNNs like transformer generalizes GNN by carefully analyzing pairwise correlation between every node to deal with limited graph topology. By a single self-attention layer, transformer can potentially allow all the nodes of an input graph to communicate. However, the price to pay is that this core component does not take any topological structure of the graph into account. Besides, the time complexity of the transformer is order of number of vertices squared times d, and d is just the feature dimension, thus limiting the applicability of the transformer, especially in a large graph. Therefore, for a large graph, one can utilize the random walk to sample a subset of nodes instead of considering the entire graph. Random walk self-attention is like this. This is a random walk self-attention. We have, with the same analogy to transformer with a queries, keys, and values. Now we are attending to different parts of the graph. But f sub j here, look at this f sub j. This one is the weight of the self-attention mechanism. We can either set it to 1 or reweight the node based on occurrence of each node, which is the number of nodes on the random walk sequence over the walk length. Therefore, it is able to estimate the statistics in the graph. The occurrence of a node in the random walk reflects its importance. Since it's challenging to model topological information by transformer, we utilize random walk encoding, which maps the distance between sampled random walk to a scalar. So the edges may also consist of rich contextual features. Edges represent the bonds between the node pairs and have features to describe the type of the bonds in a molecule graph. Similar to random walk encoding, which use the shortest paths. In the random walk, instead of fixed shortest paths in the graph for each node pair, given a shortest path for v sub I to v sub j in the random walk, which represents the set of edges linked v sub I to v sub j in the random walk sequence, we define the path features as follows. Look at this. E and W, they are features of the edge and trainable vector. The random walk encoding row, this row, and path features serve as a bias term in the self-attention mechanism, which can utilize both topological and contextual information from the given random walk path. Since there are residual connections between all modules, if the node does not exist in the random walk sequence, it will not be updated in this layer. This is interesting. So you see the differences between this approach and the transformer. In other words, the embedding of those unsampled nodes are the same in the next layer. This is very interesting, and also very bio-inspired. It looks like what we see in our brain. But of course, our brain is asynchronous, is spiking, and much more complex. Compared to transformer, which models the global interactions, CNNs exploit local features and is used as a de facto computational block with a shared kernel. So inspired by this article that I've explained it in our part 124 of this playlist, we adopt random walk convolution to iteratively update node embedding from random walk sequence. In a case layer, random walk convolution first samples a sequence of nodes with associated hidden features. Similar to RWSAN, we also leverage the topological and contextual information from random walk encoding. So put it just together, just concatenate all of this information. This is what S is. So we process hidden features of the random walk sequence with just 1D CNN with kernel size W. And this is just the Hadamard product between input features. So it gathers motive information by performing a convolution operation over the given random walk sequence, where the kernel in the CNN acts like a graph kernel and slices over the walk to extract features from each segment as motive. You see that we can assume a kernel size of 4 by sampling random walk, which is the red one, and processing the line graph with the convolution operation. It can discover several motifs in the graph. So to derive the whole graph embedding, one straightforward method is to sum the embedding. However, the direct summation treats each node equally, thus leading to oversquashing. We employ the virtual node, which is a special node that connects all the nodes in the graph and can help nodes to exchange information effectively, and thus improve the performance. This is the algorithm that for random walk conformer that I've explained. It just gives us the final embedding of the virtual node. And then they did experiments on protein, NCI1, MUTAG. We use these for graph classification, and you see an improvement, except for NCI1, that even a WR kernel approach is much better, 4% better than this random walk conformer. So the reason could be because of the distribution of the graph and many different reasons, domain shift, many different reasons.